All right, eighth grade, we have finished up forces and Newton's laws, and we're now moving into the concepts of work and power and eventually energy. And so then following this unit of work, power, and energy, we will be coming to a conclusion in our physics part of the year, taking everything that we have learned about speed, acceleration, velocity, forces and motion, Newton's laws, work, power, and energy, and putting that all into a project that we'll be working on in January. But for now, let's take a closer look at these ideas of work and power. So really, what is work, right? What is work? Let's say for a second that I give you 75 pages to read in your science book by tomorrow. Yeah, a lot of fun, right? Is that a lot of work? Well, seems like an awful lot, especially compared to the amount of homework that I typically give you. But according to science, no. No, it's not a lot of work at all. According to science, work is the transfer of energy to an object by using a force that causes the object to move in the direction of the force. So again, it's transferring energy to an object. It transfers the energy by using a force, and it causes the object to actually move in the direction of the force. So really, if I asked you to read 75 pages in your science book by tomorrow, the only work that you are actually doing is the flipping of the pages. And reality is that is not a lot of work. So if that's not a lot of work, what exactly is work? Well, let's start by just talking about real quickly some things that maybe are fun, but according to science would be considered work. We don't typically think of work as being a lot of fun, but in this case, here are just a few ideas: bowling, baseball, football, mini golf, tug of war, a water balloon fight, and I'm sure you could think of a lot of other things as well that we might think of as being fun, but in science, it's work. Or we could name some things that seem like a lot of work to us, but according to science, are not actually work, or at least not very much. Things like maybe writing a paper, or memorizing the periodic table, or perhaps coming up with a good idea for a project. These might seem like a lot of work for us, but according to the science definition of work, it really isn't a lot. So, the definition that we would have for work is anything where a force is being applied to an object, causing it to move. All right, so we talked a minute ago about the fact that work involves a transfer of energy. And so if that's the case, what exactly do we mean by a transfer of energy? Well, one way that you can tell that the bowler has done a lot of work, the bowler in this picture, is that the ball now has what we call kinetic energy. Kinetic energy is the energy of motion, or energy that is in motion. Some examples of kinetic energy would be things like a rock falling off a cliff, a football flying in the air, a pencil dropping to the ground, or a bat swinging through the air. Any of these would be considered kinetic energy. The energy of that motion is kinetic energy. So, what is the difference between force and work? We've talked a lot about forces back when we were talking about Newton's laws and things. Now we're talking about work, and there is a relationship between them, but there's also some differences. For instance, all right, so we've got a picture here of a guy who is applying a lot of force to this car. He is pushing with all his might. He is applying a lot of force, but the car's not moving. It's just sitting there. So would this be considered work according to science? Well, it would not, because we know that work involves an object moving in the direction of the force, and in this case the car is not moving in the direction that this guy is pushing. So you can apply a lot of force to an object, but if the object isn't moving, then no work is actually being done, which again seems odd. I mean, this guy, assuming it's a fairly warm day, perhaps he's perspiring, breathing heavily because he is applying so much force, and we might say he's working hard, but according to science, he is not. All right, so again, in order for work to be happening, the motion of the object has to be going in the same direction as the force that was applied to that object. So let's take a look at this. Imagine you're late for a flight to Florida. Nice. Wish I was going to Florida. You're in the airport with your suitcase in your hand, running to get on your plane. Because you're making the suitcase move, you're doing work on the suitcase, right? No, you're not. Wrong. So for work to be done on an object, the object must move in the same direction as the force that was applied. You are applying force to hold the suitcase up, but the suitcase is moving forward. So no work is being done, at least not by you, on that suitcase. There was only work being done when you lifted it up off the ground. I know. Seems weird, right? But it all has to do with the definition of work versus the definition that we use in common English. All right, so when is work done? Well, to kind of recap, work is done on an object when two things happen, and both of these things have to happen. The object moves as a force is applied, and the direction of the object's motion is the same as the direction of the force. So let's take a look at some examples. All right, here we have somebody pushing someone else in a box. A little silly, but so we have it. All right, the direction of the force is to the left. The direction of the motion is also to the left. So is work being done? Absolutely. Another picture. All right, here we have a rather ridiculous picture of somebody picking up, I don't know, a box, a stack of paper, something. All right, so the direction of the force, it's a lift upward, so the force is up. The direction of the motion, well, the papers or whatever it is being lifted up. Okay, so is work being done? Yeah, work is being done, scientifically speaking. All right, we have a third picture here. In this particular picture, the force is being applied up, holding the box up in the air, keeping the box up in the air. The direction of the motion, well, the box is moving to the left. All right, so is work being done on the box in this particular case? No, it is not according to science. So it is possible to calculate work. There is a formula for work. So the amount of work, and that's signified by a capital W, being done in moving an object can be calculated by multiplying the force, capital F, applied to the object by the distance, lowercase d, through which the force is applied. So here's our formula. Work is equal to force times distance, or we could say W equals FD. We don't necessarily need the multiplication symbol in there. We measure work in joules. A joule is actually a Newton meter. Okay, a Newton times a meter. So our forces, of course, are measured in newtons. We learned that in our previous unit, and distance is measured in meters, or calculated in meters. So let's try one. How much work is done when a 1 Newton force moves a block 59 meters? Well, we know that the formula is work equals force times distance. So 100 newtons of force times 59 meters of distance gives us a measurement of work of 5,900 joules. Okay, remember the unit for work is joules, and Newton times a meter is a joule. All right, so we've taken a look at work. How about power? Okay, how about power? Power is how fast work is done. So the rate at which energy is transferred would be the more official way to say it. And we just talked about the fact that work is a transfer of energy onto an object. So essentially, it's the rate at which work is done, or the rate at which energy is transferred. Same thing. Again, we can calculate power also. So to calculate power, we divide the amount of work done by the time it takes to do the work. So our formula for power is power equals work divided by time. And power is actually measured in a watt. All right, it's joule per second. So it's measured in a watt. The work, of course, is calculated in joules and time in seconds. So let's practice power. Again, power is how quickly work is being done. So we've got a stage manager at a play, raises the curtain on the stage by doing 5,976 joules of work on the curtain in 12 seconds. What is the power output of the stage manager? Well, in order to calculate power, we need to do work divided by time. In this case, the work was 5,976 joules. We're going to divide that by the time it took him to do that work, which was 12 seconds. And if we calculate that, we come out to an answer of 498 watts of power. All right. Watts are often talked about in terms of, light bulbs and things of that sort. So you can kind of think of it that way. You might use a 100-watt bulb in a lamp at home. Well, here we have a stage manager that, at least for a period of time, is using 498 watts of power. All right, ladies and gentlemen, like I said, make sure you hold on to these notes. You're going to be referring to them for the next few weeks, including into the month of January when we work on our project. Have a great day, guys. See you later.